Hello everyone, welcome to the course Fundamentals of Manufacturing Processes. In week 11, we'll talk about heat treatment processes. This course is offered by Professor D.K. Dwivedi from Department of Mechanical and Engineering, Industrial Engineering, IIT Roorkee. I'm your TA Alka Jangir from IIT Kanpur. First, we'll go through some sample assignment questions which will help you in solving your weekly assignments, and then we'll go through some lecture notes. So first question is, the welding defect of lack of penetration can be taken care of. Your options are by increasing welding speed, by increasing the current value, or by increasing the current by reducing the current value, or by opting low heat energy sources. So in previous lecture we talked about how with changing the welding method such as laser beam or plasma welding, all those you can change the heat energy source. So by opting for low heat energy, you will be requiring more time for the welding. So which option would be correct? Among these, the answer will be increasing the current value. Okay, so incomplete penetration occurs when the weld bead does not reach the root of the joint of the weld on the opposite surface in the part. To correct this discontinuity, you can increase the current, decrease the welding speed, or change the joint geometry. Increase the average current setting on the welding power source, or avoiding molten pool from the flooding the weld. Can also use a suitable diameter electrode and the correct welding current. Okay, so increasing welding speed will only reduce the penetration. So you have to decrease the welding speed. So longer the time you take at a place, then it will have more time to penetrate the entire thickness of the weld. Second question is the welding defect which causes a reduction in the cross sectional area and so reduces the strength of the welded joints. Your options are residual stress, distortion, undercuts, or misalignment. So these are various welding defects, so you need to remember the definitions and their respective images. So using that you can remember what are the correct definitions, so you can answer these questions easily. So in this question answer will be undercuts, C. Okay, so undercuts looks like this one. So here your surface area won't be proper compared to the base metal. So undercutting is a welding defect which reduces the cross sectional area of the base metal, which in turn weakens the weld and workpieces. Undercutting is most common in lap fillet welds but can also be found in fillet and butt joints. Undercutting can be caused by excessive current, so the edges of the joint melt and drain into the weld, leaving a drain-like impression. Or it can be due to poor technique. So in this case, not enough filler metal is deposited along the edges of the weld, or incorrect filler metal, in which it creates greater temperature gradients between the center of the weld and the edges. Fourth is incorrect angle, so directs more heat to the free edges, or too large of an electrode which can cause undercutting, or incorrect usage of gas shielding, so it can also cause undercutting. Okay, so these are the various reasons. Next question is, the strengthening mechanism leads to the hard face formation due to the heat treatment of the steel is. Your options are solid solution hardening, hardening or strengthening, grain refinement or transformation hardening, or the dispersion hardening. So you should know about all these strengthening mechanisms as well. So in case of solid solution strengthening, you will be adding some alloying element which can either go in interstitial or at substitution sites, and it will be providing some strain in the lattice, which will be interacting with the moving dislocations. So that will lead to strengthening in the alloy compared to the pure metal. In case of grain refinement, as you keep on reducing the grain size, your dislocations in the N metal will face more of the barrier to the free movement. So it will also cause strengthening. In case of transformation hardening, what will occur? You are transforming one phase to another and choosing a phase which can have higher strength. Dispersion hardening, in this case you will be having dispersoids, which can be oxides or nitrides, or can be any type of different phases, which will be again acting as a barrier for dislocation movement. So in this case, correct answer will be transformation hardening. Okay, so here what's occurring? You have hard phase formation due to heat treatment. Okay, so entire phase is changing. So in case of transformation hardening, which is also known as quench hardening, is a process which improves the mechanical properties of steel by rapid quenching a heated steel surface. Okay, the process involves a diffusion-less martensitic transformation, which occurs when steel is quenched too quickly from the austenitic phase. Here are some ways to transform the surface microstructure of steel. First is laser transformation hardening, where a widely used surface modification technique which uses a laser to modify the surface of selected steels. This process offers many benefits, including a clean manufacturing environment, high volume and minimum distortion. Next is friction transformation hardening. In this case, a process which involves heating a material with friction. It can be used on flat or curved surfaces, and it is suitable for medium carbon and high carbon steels and a range of low alloy steels. In case of flame hardening, an inexpensive and flexible process which uses a flame gun to heat the surface. However, it is slow, difficult to control and not easily automated. Next question is, the annealing and normalizing is done above lower critical temperature, or above upper critical temperature, or above eutectic temperature, or all of these. So correct answer in this case will be above upper critical temperature. Okay, so in phase diagram, this is what it looks like. So the red part, the shaded red part, is the temperature chosen for soaking and for full annealing, and for normalizing it is shaded with the light blue. Okay, so in both cases you can see it's above this A3, which is upper critical temperature, above this part. Okay, so the correct answer will be above upper critical temperature, and your eutectic temperature here is this, corresponding to this line. Above this you will be having liquid as well, so you never go in liquid phase in case of annealing and normalizing. These heat treatments always deal with the solid alloy. Okay, so in full annealing it produces a softer microstructure. The temperatures for full annealing are typically 50 degrees Celsius above the upper critical temperature A3. For hypoeutectoid, so hypoeutectoid, you mean by this that eutectoid reaction takes place at 0.8% carbon. Okay, so if a composition of carbon is lesser than 0.8%, then you will be having hypoeutectoid steel, and if it's above 0.8, then it will be hypereutectoid steel. Okay, so here for the hypoeutectoid, you are heating above A3. A3 is this line where your proeutectoid ferrite and pearlite entirely converts into the austenite, and here ACM line is where cementite, proeutectoid cementite converts into the austenite. Okay, so in case of hypoeutectoid, you heat above 50 degrees Celsius above A3, and in case of hypereutectoid steels, you heat it to the lower critical temperature A1. So above A1 you heat in case of full annealing. Okay, so temperatures for normalizing are approximately 55 degrees Celsius above the upper critical line. The normalization temperature is higher than the temperature for full annealing. On the other hand, the cooling is more intense. Normalizing improves the machinability of a component and provides dimensional stability if subjected to further heat treatment processes. Okay, so normalizing forms fine pearlite basically, and it also reduces the formation of the continuous layer of the cementite, proeutectoid cementite. So that's why it improves the machinability. The main difference between the annealing and normalizing is that annealing allows the material to cool at a controlled rate in the furnace, while normalizing allows the material to cool by placing it in a room temperature environment and exposing it to the air in that environment. So cooling rate is always higher in case of normalizing compared to annealing. Because of the higher cooling rate, you will be having non-equilibrium microstructure in case of normalizing compared to annealing. Okay, and here, okay, next stress relief I think will be talked further. So in question 5, correct statement regarding the effect of soaking temperature during normalizing of steel on grain size is: higher the soaking temperature, the finer the grain. Higher the soaking temperature, the coarser the grain, or the lower the soaking time, the coarser the grain, or the lower the soaking temperature, the coarser the grain. So as you know, with increasing temperature, you will be having more activation energy for the coarsening of the grains. Okay, so higher the soaking temperature, coarser the grain will be the correct statement out of all these 4. Okay, so here also you can see with increasing temperature, the grain size is increasing. So it is given in micrometer. So it's changing with increasing temperature, and with increasing time as well it is increasing. So if you give more time for coarsening, the more diffusion will be there and more coarsening will be there. So in explanation we can see higher soaking temperature can result in coarser grains, increasing soaking time. So at a given temperature, increasing the soaking time, here you can see at 1175 with 3 different times, you can see with increasing time you are seeing higher grain size. So increasing soaking time will increase grain size. This is because more grains are formed during the soaking time. Increasing austenizing temperature. So increasing the austenizing temperature will increase the average austenite grain size. Increasing hardening temperature. So increasing the hardening temperature and soaking time will increase the grain size and hardenability. and this is because the grain size increases with higher temperatures and longer soaking times. Next question is the temperature range in the heat treatment of steels for stress relieving purposes. Your options are 1050 degrees Celsius to 1150 degrees Celsius, 600 degrees Celsius to 650 degrees Celsius, or above 1200 degrees Celsius, or below 500 degrees Celsius. So in case of stress relieving purposes, it's done below a lower critical temperature. So correct answer will be B, 600 to 650 degrees Celsius. Okay, so A1 here is the lower critical temperature. So below this, it's shown here, lower critical temperature is your 723 degrees Celsius. Okay, so above this, some of the perlite, your perlite will convert into proeutectoid phases or in austenite. Okay, so here you're heating it below this part, so there won't be any microstructural changes, just relieving of stresses, so dislocation will get annihilated. The temperature range for stress relief annealing of steel is usually between 550 degrees Celsius to 650 degrees Celsius, and the exact temperature depends on the composition of the steel. Okay, so the stress relief annealing is used to relieve stresses from cold working. In contrast to process annealing, this heat treatment is usually performed after the product has been made. Care must ensure uniform cooling, and particularly when a component is composed of variable section sizes. If the rate of cooling is not constant and uniform, new residual stresses can result in equal to or greater than those that the heat treating process intended to relieve. The annealing temperature is typically relatively low, such that effects resulting from cold working and other heat treatments are not affected. Stress relief heat treatment can reduce distortion and high stress from welding that can affect performance. Next question is weldability of metal depends upon. Your options are thermal conductivity of material, thermal coefficient of expansion, melting point temperature, and density. And your options are 1 and 2, combination of 1 and 2, 1, 2, 3, or 2 and 3, or 1, 2, 3, 4, all are correct. So which one should be the correct answer? So density is not affected, it won't affect your weldability, density of metal, and other than those, all these three are correct options. Okay, so materials weldability, also known as how easily it can be welded without defects, depends on a number of factors including materials property such as a metal's melting point, thermal conductivity, its reactivity to gases surrounding it, the coefficient of thermal expansion, all affect its weldability. So all these three are here, and materials with medium melting points, low thermal conductivity, low reactivity and low expansion are more weldable. Welding method. So the welding method used can affect the weldability of a material. Some welding processes work better for certain materials than others. Or welding parameters. The quality of the weld can vary depending on parameters such as the electrode material, shielding gases, welding speed and cooling rate. Shape of the parts. So the shape of the parts to be welded can also affect the weldability. Next question is the most effective strengthening mechanisms in case of heat treatable aluminum and copper alloy is? Your options are solid solution hardening, grain refinement, transformation hardening and precipitation hardening. So the correct answer will be precipitation hardening. Okay, so in case of aluminum copper, you when you see its phase diagram, you will be seeing there will be formation of precipitates. So the precipitation hardening, also called edge hardening or particle hardening, is a heat treatment technique based on the formation of extremely small, uniformly dispersed particles, precipitates of a second phase within the original phase matrix to enhance the strength and hardness of some metal alloys. Second phase particles present further types of obstacles for dislocation moment. The presence of a second phase particles represents a distortion in the matrix lattice. Therefore, the obstacles that hinder the dislocation motion are either the strain field around the second phase particles or the second phase particles themselves, or both. Precipitation hardening increases the yield strength of malleable materials, including most structural alloys of aluminum, magnesium, nickel, titanium and some steels and some stainless steels. In super alloys, it is known to cause yield strength anomaly, providing excellent high temperature strength. And in the case of aluminum alloys, precipitation strengthening can increase the yield strength of aluminum from about 5 times up to about 15 times that of unalloyed aluminum, especially 2XXX series. So in this case, these are alloys with the copper, your aluminum alloy with the copper, which can be precipitation hardened to strains comparable to steel. Okay, so this strength can be achieved because of the precipitation hardening, because of the precipitates that will be formed of aluminum and copper. Ninth question is the heat treatment process used to produce the effect of strain hardening during cold working processes. Your options are spheroidized annealing, process annealing, full annealing and intercritical annealing. So the only annealing that is done during the process, it's process annealing or in process annealing. So this one would be the correct answer. So here the temperature ranges are also told for these processes. So normalizing and full annealing we already saw. Spheroidizing is done below lower critical temperature, and partial annealing is done in between spheroidized and normalizing temperature. This is full annealing temperature, and this process annealing is done for only these composition of steels up to around 0.3% carbon percent of steels. Okay, so process annealing, also known as subcritical annealing or intermediate annealing, is a heat treatment process which improves the properties of metals and alloys. Its purpose is process annealing improves the cold working properties of low carbon steels and softens high carbon and alloy steels. It can also relieve internal stresses, restore ductility and make parts more workable. The process involves heating the metal or alloy to a predetermined temperature, holding it for a set amount of time and then cooling it to the room temperature. The range for process annealing is typically between 260 degrees Celsius to 760 degrees Celsius depending on the alloy. Process annealing is mainly used for low carbon steels such as cold rolled steels, wire drawn steel and centrifugally cast ductile iron pipes. Benefits: so process annealing can improve ductility and reduce brittleness. So when you are performing cold working, then it's more likely to become brittle because of the accumulation of dislocations and because of residual stresses. So it can also help restore ductility that has been lost through repeated hammering or other working. So because of this type of annealing, there will be annihilation of dislocations and reduction in stresses. 10th question is the reason for using normalizing heat treatment on steel is. Your options are reduction of residual stresses, refinement of grain structure, or increment of the residual stresses. So the possible answers are 1 or 2 only, 1 only, 1 and 2. So we are going through sample assignment questions. So this question is 10th question is the reason for using normalizing heat treatment on steel is. Your options are reduction of residual stresses, refinement of grain structure, or increment of residual stresses. And your options are 1 only, 2 only, 1 and 2, and 1, 2, 3. So in case of normalizing steels, it provides advantages of both reduction in residual stresses as well as refinement of grain structure. And this one is incorrect statement, increment of residual stresses. So 1 and 2 will be the correct option. So in case of normalizing, it is a heat treatment process which has advantages such as it produces stronger metals compared to annealing, because in this case you are using cooling rates which are higher than annealing. So there will be formation of non-equilibrium phases which have higher strength compared to equilibrium structures. Normalizing also removes internal stress from metals which can cause failure if left untreated. Normalizing improves the uniformity of the material. Normalizing can also increase the durability of a material. Structural stability. So normalizing can improve the structural stability of a material, and normalizing can also help a material regain its ductility and softness. Normalizing is less expensive compared to annealing, because in case of annealing you will be requiring more time, more usage of furnace, because furnace cooling is used in annealing, while in case of normalizing, during cooling part you will be putting your material in air, so it will be less expensive. Widely used, normalizing is one of the most common industrial processes for metals. Normalizing is used for hot rolled products like bars, railroad wheels, and forged steel products. Now we'll go through some lecture notes. So first lecture is weldability and welding defects. So in case of weldability, it can be defined as the ease of the welding. So how easily you can perform welding on a particular material without having any defects. So if there are a lot of defects in the material, then it will be a material with less weldability. It is characterized by cost of producing the weld. So if the equipments that are required or the type of welding that is required, if those are cost effective, then it will be higher weldability. Quality of weld joint. After welding, the joint quality should be good. So the strength of the weld joint and the heat affected zone should be lesser. All these are the some of the properties of a good weldable materials with good weldability. Efforts for producing the joint. So efforts required are also less in case of good weldable materials. Weldability of steel. It is characterized by cleanliness of the weld. So after welding, the weld that you are getting, its cleanliness would be higher if your weldability of steel is higher. Hardenability of steel will also be affected. So if your material is very hardenable, so it is more likely to create martensite in that particular part where you are performing welding. So if it is forming martensite, then there will be non-uniformity in the strength across the cross section. So that's why hardenability also plays an important role in weldability. Now, effect of properties on weldability of metals. So in case of chemical properties, if your material's chemical composition, this will affect weldability. For example, in case of steel, with increasing amount of carbon or chromium, you will be having, if there is more carbon and chromium, it will be having less weldability because of the formation of chromium carbide, which will cause it to sensitize. Oxidation. So if your material is more prone to oxidation during welding, so it will be having less weldability. Evaporation. So if it has a phase which is more likely to evaporate, then it will be less weldable. Affinity with the atmospheric gases. So if your material at a higher temperature, then it can react with nitrogen and oxygen, then it will be forming some oxides and nitrites. So those inclusions, they can lower the strength of material. Structure of the metal. So in what structure you are using your material for welding, that will also affect weldability. Mechanical properties. So yield strength of material and percent elongation, ductility and toughness, these properties will also decide weldability of metal. Physical. Thermal conductivity. Thermal conductivity of steel, how easily the heat will be dissipated from the welding part. Coefficient of thermal expansion, so this should be lower. Your material should not expand much, otherwise it will show distortion. Solidification temperature range, so this range should be lower. Melting point should be higher, or depending on which type of welding you are choosing. If it's lower, then for example in case of aluminum and all, it becomes critical to do welding. Iron carbon diagram. So in case of steels, we'll be using this particular diagram. So you should know at least what are the eutectic composition, and around up to eutectic reaction, up to steel part will be up to 2.1%. So this part you should remember for understanding which phases will form. Then CCT diagram. So this is continuous cooling. So in this case you are having this particular diagram. So in this case you are using continuous curves. Okay, so these continuous curves will show like which type of final structure will be forming in steel. Okay, so depending on various methods of cooling, so if you are water quenching your steel, then you are using very high cooling rate. So in this case you are forming on complete martensite. If you are cooling it with the critical temperature, which is it's just touching the nose temperature, then it is for critical cooling rate. So here you will be again forming martensite. If you are having a cooling rate lower than the critical cooling rate, then you will be forming martensite plus pearlite, and lower than that you are getting fine pearlite, and then more lower On the lower side you will be getting coarse pearlite type of structure, which is in case of full annealing. In case of normalizing you are getting fine pearlite. And MS is the martensite start temperature, so 220 degrees Celsius. If you don't touch this CC diagram, then if you enter this 220 degrees Celsius, then below this it will start forming martensite. So it will be temperature dependent process. Next is stainless steel classification. So there are based on microstructures. It is ferritic, austenitic and martensitic type of stainless steels, and these will, so the microstructure which will be there, it will be defined by the alloying elements that are added, which are shown here. So if you have higher amount of nickel this nickel equivalent, so here the nickel, carbon and manganese, these three elements these all presence of these will lead to formation of more austenite. And if there is presence of chromium, molybdenum, silicon and niobium, then it is more likely to form ferrite. So based on these you can find out at what percentage you will be getting ferrite or austenite or martensite. Problems in welding of stainless steels. So there can be solidification, cracking, there can be weld decay or sensitization. Sensitization will be formation of chromium carbide. Hairline or knife line type of cracking, sigma phase formation. Typical heat affected zone of low carbon steel. So you are performing welding along this center line. I'll use laser point. Okay, so your center line is here. So you are providing the direct heat up to here. So the highest temperature will be here, and as you move to this side, your heat provided will be less and less. Okay, so here you will be having temperature up to melting temperature of steel. So here you will be having gamma phases as well, gamma phase as well as the delta iron as well. Okay, so as you keep moving to this side you will be having gamma and also alpha phases. So as you move to this side you will be having these various phases where grain growth zone is there, recrystallization zone, partial transport zone, tempered zone and unaffected base material. Okay, so based on that it's the coarsening will be here. So here the crack initiation is mainly in these portions where you have coarsened grain size. Problems in welding of aluminum alloys. So in this case you have solidification cracking, partial melted zone cracking, residual stresses, distortion and wider heat affected zones, affinity to atmospheric gases. So here as you know aluminum has high affinity to oxygen as well, oxygen and nitrogen. So it's more likely to form oxides, and porosity in the weldment. Now the solidification cracking, it occurs at the last stage of solidification and center line of the weld. Factors which affect solidification cracking. So these are various factors. So solidification temperature range. In case of here you can see the solidification. So here you have complete liquid and here you have complete solid. So if you have some other alloys, so it will be having this type of phase diagram, then up to here you have higher solidification time compared to here up to this composition where you have very smaller range. Okay, so based on this also your solidification cracking changes. Amount of low melting liquid. So if you have two types of alloying elements or two types of metals, so if you have an element which has low melting point, so amount of that element will also decide the solidification cracking. Distribution of film and layer, grain orientation, grain size, residual stresses, composition and yield strength of filler material, and weld width geometry. These all will decide solidification cracking. Next is factors which affect residual stresses. So for a material, coefficient of thermal expansion, melting point, weld joint design, welding sequence, and welding processes. These all will affect residual stresses. Effect of residual stresses on weld joint. So this will cause lowered mechanical performance. So along the welding joint, if you will be performing tensile testing, you will be getting lesser of the strength, lesser of ductility in case of when you have residual stresses, and there will be embrittlement as well. It promotes stress, corrosion, cracking. So because of the residual stresses, there will be corrosion along those places as well. Lower down fatigue performance in case of tensile residual stresses. So you must already know that if there are tensile type of residual stresses, then it always lowers the fatigue performance, while in case of compressive type of residual stresses, it improves the fatigue performance. Because fatigue, when we consider fatigue type of loading, then we mainly go for the loading which are of tensile types or at the neutral line. Next is location of cracks. So weld metal cracks, toe cracking, heat affected zone cracking, and crater cracking. So these are depending on location of cracks. And unfavorable mechanical properties. So if your material has these type of properties, then it is more likely to undergo fracture. So if it has very high hardness, if it has very high yield strength, if it has limited ductility and low toughness. So toughness is the amount of energy that is absorbed before the fracture. So if it is less, then your crack will propagate very faster. Next is lamellar tearing. It is based on these locations: cold cracking, and then next chapter is heat treatment fundamentals. So first is heat treatment process. So it can be defined as the heating of material, then soaking and holding at that particular temperature, followed by controlled cooling to alter the properties of material, okay, to obtain either desirable mechanical properties or for the desirable conditions such as relieving internal stresses. Mechanical properties can be better machinability, such as in case of normalizing you get better machinability, improved ductility, and homogeneous structure. Purpose of heat treatment. So it causes relief of internal stresses developed during cold working, welding, casting and forging, etc. It also hardens and strengthens the metals, improves the machinability, changes the grain size. For example, in case of normalizing, you get lower grain size, or in case of quenching also you get lower grain size than the grain size that you initially start your material with. It softens the metals for further cold rolling. So in case of process annealing, you provide annealing so that you can further reduce the thickness of material. Okay, as in case of wire drawing and cold rolling. It improves ductility and toughness. It also increases heat, wear and corrosion resistance of materials. It also improves electrical and magnetic properties. It homogenizes the structure to remove coring. So the annealing, which is homogenization, for homogenization at very high temperatures, at very high timings, it is homogenization type of annealing. So in that case you homogenize your structure because of the, after casting you get a structure which will be having composition which is very distribution is very non-uniform. Spheroidize tiny particles such as those of cementite in steel. So it occurs by diffusion. So homogenization annealing is also known as diffusion annealing. Fundamental diagrams. So these three diagrams which are of very importance in case of studying heat treatments. One is iron carbon phase diagram, iron carbon or iron carbide diagram, time temperature transformation, continuous cooling transformation diagram. First we have iron carbon diagram. So this is plotted up to 6.7%, which is a composition of cementite. Okay, and here this circle shows the composition up to steel, and after this you have cast iron. And this diagram again, it is for steel, heat treatment of steels, and the temperature ranges are shown for normalizing, for full annealing and for spheroidizing. Okay, and A1, A3, A1 is the lower critical temperature, A3 is upper critical temperature, ACM is this the again upper critical temperature in case of this hypereutected steel cementite transformation. And these are the compositions that you should remember: 0.76 or 0.8%, which is eutectoid composition, then here 4.3 percentage and 1147 degrees Celsius for the eutectic point, and temperature here is the 727 degrees Celsius, which is eutectoid temperature and eutectic composition. Okay, and here you have peritectic reaction at 1493 degrees Celsius. Okay, then you have time temperature transformation diagram, which is also known as isothermal transformation diagram, also isotemperature diagram. So in this case you have this C type of diagrams which looks like C. So here, as you, in case of isothermal, meaning at a single temperature, so you will be first quenching your material, then you will be holding your material at that particular temperature for longer time, then again after the completion of transformation you will be quenching your material. Okay, so in the first four which is this cooling curve for the 4, it is the, here you will be forming complete pearlite. Okay, it will be fine type of pearlite. If you will be holding up to higher temperature, then you will be getting coarse pearlite. Okay, and as you keep on going near this nose temperature, then you will be getting finer and finer pearlite, and up to nose and below nose you will be getting bainite. Okay, so here you will be getting bainite if you will be holding your material here, and bainite will also be upper bainite and lower bainite depending on the microstructure. So lower bainite will be below and upper bainite will be at higher temperatures. Then you will be this part is the austenite. So below this temperature you are getting metastable austenite. Okay, so this austenite will be converting here into 50% of the bainite, and then remaining will be converting into martensite, because you haven't given sufficient time for conversion of entire bainite. So 50% bainite is converted and remaining austenite, metastable austenite, will convert into martensite. Okay, and here two green one, you are following this path, then you will be getting 100% martensite. And in one case of one, you are making martensite and metastable austenite. So here you haven't cooled your steel below M90, that's why you are getting 50% of the martensite and 50% will be metastable austenite or retained austenite. Next is continuous cooling transformation. So in previous case you are holding your steel at a particular temperature. Okay, in previous case you are holding your steel at a constant temperature, okay, during the transformation, while in this case your steel is continuously cooling even during transformation. So these diagrams will be slightly different compared to these time temperature transformation, because you are cooling here continuously. So in this case it is very hard to form bainite, because bainite will come below nose temperature, while in this case when you are continuously cooling your steel you can't go below nose. Okay, so you are more likely to get coarse perlite, fine perlite and mixture of perlite and martensite or complete martensite with help of continuous cooling. Okay, so these are various type of structures possible. So here if you touch this continuous cooling with the nose temperature, then it is known as critical cooling rate. So if you cool your steel below at a faster rate compared to this rate, then you will be always getting martensite. Next is the types of heat treatments that are possible for steels. So annealing, normalizing, hardening, tempering and carburizing. So compared to these, carburizing is the process which is known as surface hardening. So where you are adding some chemicals as well. So you will be adding carbon. So this is different than the other four. Okay, so here temperatures are shown for the normalizing, full annealing, hardening. In case of hardening, you are heating your material up to this part. Why? Because you don't want to convert cementite into austenite. Because the cementite has the highest hardness compared to even martensite. That's why you want to retain cementite as well in the final structure. Here you have process annealing as well and spherodizing annealing as well. Now annealing, it is performed to reduce hardness, improve machinability, facilitate cold working and produce a desired microstructure. So these are various types: full annealing, critical annealing, process annealing and spherodizing and stress relieving. Okay, and the holding temperatures are different for all these annealings. In case of full annealing, you have the highest temperatures, highest holding temperatures. Then spheroidization, stress relief and recrystallization are below upper critical temperature. Next you have normalizing. So normalizing of steel is carried out by heating above upper critical temperature, soaking there for some time and then cooling in air to room temperature. Okay, the aims of normalizing is to improve hardness and strength, to improve its machinability, to modify the grain structure. So grain structure here will be fine aqueous type of grains. Machinability will be also high here because you have fine perlite. Provide more consistent response when hardening and case hardening. So in case when you have fine perlite, then it will when you are again heating it to the hardening temperature, then it will be showing uniform properties throughout. Next is before tempering, hardening is important. So in case of hardening, the sample is heated above A3 and ACM or ACM depending on composition. Okay. To cause austenization, the sample is then quenched at a cooling rate higher than the critical cooling rate. So here to avoid the nose of the CCT diagram, the quenching process produces residual strands such as thermal and because of phase transformation. The transformation to martensite is usually not complete and the sample will have some retained austenite. The martensite produced is hard and brittle and tempering operation usually follows hardening. This gives a good combination of strength and toughness. So after formation of martensite, you will be having some retained austenite as well. So convert these phases into phases which are less brittle. You go for tempering. Okay, this is the hardening temperature which is shown here. Okay, so after this you go for tempering. In this case, it is carried out by heating the steel below lower critical temperature, held for a period and then slowly cooled in air to room temperature. Okay, so these are the after austenizing, you have quenched your material steel and then you heat it and temper it. So tempering, it will relieve the stresses, it will convert the metastable phases into more stable phases. So retained austenite will be converted into bainite and your martensite will be converted into some phases such as cement, very fine cementite and ferrite, followed by air cooling. Okay, so after this tempering, with increasing tempering temperature, you see reduction in hardness and increase in the elongation. Then you have two processes, Aus tempering and Mar tempering. These processes have been developed to avoid residual stresses which are generated during quenching. Okay, in both these processes, austenite steel is quenched above MS. MS is the this martensite start temperature to a temperature T1 for homogenization of temperature across the sample. In Mar tempering, the steel is then quenched and the entire sample transforms simultaneously to martensite. This is followed by tempering. In Aus tempering, instead of quenching the sample, it is held at T1 for it to transform to bainite. Okay, so here are the paths that are shown. So in case of Aus tempering, you're cooling your steel up to here and then you are holding it up to this point. So you are converting your material into bainite. So after Aus tempering, you don't require tempering. So that's why it's called Aus tempering, because bainite is a stable structure compared to martensite and retained austenite. In case of mar tempering, you're just holding up to here for some time, then you're quenching. Okay, so what will occur? So here during this holding, you'll be having the same temperature as on the core as on the surface. So you'll be getting a more uniform structure, and you'll be getting less stress, residual stresses. Hardening we already talked about. Then we have types of annealing. So first, annealing, it involves heating the steel to a suitable temperature, holding it at that temperature for some time, and then cooling it slowly. There are different methods of cooling. The main purpose of annealing is to reduce the hardness of a material. Besides this, it is also used to relieve the internal stress of a material, restore ductility to perform the further operation on the material, and to increase the machinability of the material, and to induce softness. These are the various types of annealing. So first is diffusion annealing, which is done at the highest temperature. In this process, hypoeutectoid, eutectoid and hypoeutectoid steel are heated uniformly, and the component is held at a temperature between 1000 to 1200 degrees Celsius, and then cooled very slowly in the furnace in order to remove the heterogeneity in the composition of heavy castings. So heavy casting meaning it's very large casting, so it is more likely to have composition distribution which is not uniform. Okay, so coring or these type of effects will be seen, and to remove those you provide diffusion annealing. During this, a coarse grain structure is produced. So this is not used as the final heat treatment process. So after this you need to provide some other heat treatment as well. So it provides a homogeneous structure. To increase material properties, it goes through full annealing after diffusion annealing. Okay, so after providing diffusion annealing, you need to provide full annealing as well to find the grain structure. Next is full annealing. One second. So in case of full annealing, it consists of heating the steel component to about 50 degrees Celsius to 70 degrees Celsius above the critical temperature, holding it for a sufficient length of time and cooling the same in the furnace. It is adopted for steel casting and ingots, and the coarse structure produced during solidification break down to a much smaller size. The machinability and ductility increases and hardness is reduced. In this case, all structural imperfections gets removed. Next is ferrodized annealing. In this method, heating can be done in three ways. So first is it can have prolonged heating just below the lower critical temperature, followed by relatively slow cooling. It can have alternatively heating and cooling the workpiece to just above and below the lower critical temperature. It can have short heating at a high temperature followed by relatively slow cooling. And it can have conversion of hard lamellar or network carbides of high carbon steels into globular or spherical shapes. It can improve machinability and ductility. So when the cementite is not in form of lamellars but in form of spheroids, then it will show improved machinability and also improved ductility. Process annealing. This process involves heating of steel to a temperature just below the lower critical temperature 723 degrees Celsius of steel. It's usually cold work steel has high hardness and low ductility, making it difficult to work. The deformed grains in cold working get reoriented, hardness is lowered and ductility also increases. Next chapter is annealing, normalizing and hardening. So first, triple T diagram for 1.13 weight percent carbon steel. So 1.13 weight percent carbon steel will be having hypereutectoid type of steel. So it will be forming proeutectoid cementite before formation of pearlite. Okay, so for iron carbon alloys of other compositions, hyper and hypoeutectoid steels, a proeutectoid phase exists. Hence, there should be another curve describing that reaction. This figure shows IT diagram for a hypoeutectoid steel which forms a proeutectoid cementite phase. Now, in this case, you are getting in this part you are forming cementite, this red part, and after this red line to green line you are forming pearlite. Remainder of the austenite converts into pearlite, where this austenite will be having composition of eutectoid steel. Okay, so and this cementite will start forming even above eutectoid temperature. This is the TTT diagram of 4340 steel, which will be having magnetic bay as well. Now, effect of different cooling grades. Okay, so here various cooling curves are there, so we'll talk about them. So first cooling curve is 1. Okay, so x1 to x dash 1 up to this part. So in this one, what's happening? The transformation begins at x1 and finishes at x1 dash. It is similar to annealing. Here it forms coarse pearlite. Okay, so as I told you earlier, this part is coarse pearlite and this part is fine pearlite. Then you have upper bainite and lower bainite here. Okay, then you have martensite here, martensite finish. So it forms coarse pearlite. There is a slight change in size of pearlite that forms at the beginning to the end due to slight change in temperature. So as the temperature keeps on changing, it will reduce the size of the pearlite grains. See, the transformed product is relatively soft, having the Rockwell hardness at the C scale up to 15. After x1 dash, the sample may be cooled down to room temperature rapidly, as there will be no further transformation. So this is useful in case of industries. Next we have second curve. So cooling curve 2, here you are cooling x2 to x2 dash, and here you are forming medium pearlite having Rockwell hardness up to 30. Okay, so here transformation begins at x2 and finishes at x2 dash, and here it describes isothermal annealing. Okay, isothermal because you are holding it at a constant temperature. It is uniform, coarse pearlite, microstructure and hardness. You will be having more uniform. When you will be cooling with the isothermal cooling, then you get more uniform structure. The transformation finishes at a much shorter time scale than case 1. Okay, so here you had completed here, but here you are completing at a time here. So here time is in log scale, so the difference may look here smaller, but it is higher time difference because it is in log. So here you will be having uniform, coarse pearlite, microstructure and hardness, and the transformation finishes at a much shorter time scale compared to case 1. Okay, then we have cooling curve 3. Here you have much faster cooling than annealing. Okay, so compared to previously, so it is typical of normalizing. Here transformation starts at x3, indicating formation of coarse pearlite in much shorter time than annealing. It finishes at x-3, forming medium pearlite. Okay, and it has larger temperature difference between x3 and x3 dash. The structure shows greater variation in fineness of pearlite and smaller portion of coarse pearlite than the annealed sample. Next you have cooling curve 4, which has much faster cooling rate than normalizing, and it uses slow oil quench. So in this, microstructure will be a mixture of medium and fine pearlite. Okay, so here x4 dash, it transforms, starts at x4, stops at x dash 4. Okay, so here you will be having combination of fine pearlite and medium pearlite. In case of fifth one, you are cooling at very faster rate. So typical of intermediate cooling rate, starts transforming to fine pearlite at x5 in relatively short time. Transformation to fine pearlite continues until curve becomes tangent to some percentage transformed. Here 25% at x5 dash. Below this curve, the cooling curve is going in the direction of decreasing percentage transformed. Okay, and transformation stops with further cooling until it hits this x double dash 5. Okay, so here remainder of the austenite, it converts into martensite. The remaining austenite would transform to martensite. The microstructure will be having 25% of fine pearlite and 75% of martensite. Next is cooling curve 6 and 7. Okay, so 6 and 7 both will be having martensite formed. So it is typical of drastic quench which misses nose region. It remains austenitic until MS, here up to here, and then transforms to martensite. 100% martensite of high hardness will be forming. Cooling curve 7 is the critical cooling rate, below which there is either pearlite or banetic transformation. Okay, so this is the critical rate where it will be touching this nose, and if you cool slower than this, then you will be going in this zone, having banite formed as well, banite or pearlite form. Cooling curve 8. So 8 is cooling up to here, then isothermally holding here and then cooling. So here you will be getting 100% banite. Okay, so cooling rate is similar to 6, but at 8 holding at a constant temperature, and it starts to transform into banite. In order to form complete banite, you can cool at a faster rate to miss the nose and then hold it at a constant temperature for a sufficiently longer times. Okay, so here you are getting lower banite and its hardness is up to 60 in C scale, at Rockwell C scale. And this hardness is lesser compared to martensite. Martensite will be having around 65. Previously we had the isothermal type of cooling. Here we have continuous type of cooling. Okay, so transformation on continuous cooling. So these are isothermal diagram which can't be used when the cooling is done continuously. Okay, so previous diagram can't be used in continuous cooling. The diagram must be modified for transformation which occur as the temperature is constantly changing. For continuous cooling, the time required for a reaction to begin and end is delayed. Okay, so why? So here in solid line you can see continuous cooling curves, and with the dashed line you can see the triple T diagram. So in this case, if you are cooling with the continuous cooling, then you will encounter this solid line one, continuous cooling transformation curve. So in case of isothermal cooling, what occurs? You are quenching your material and you are holding it with the at a constant temperature. So at a particular temperature it is spent more time compared to when it is in continuous type of cooling. That's why this curve is always shifted to the right side and to little lower of the temperatures and higher times. Okay, so transformation takes higher time compared to isothermal. Here for continuous cooling, the time required for a reaction to begin and end is delayed. Okay, and the diagram must be modified for transformation that occurs at the temperature is constantly changing. The diagram is called the continuous cooling transformation, CCT type of diagram. The MS and MF line occurs at the same temperature for IT and CCT diagram. MS and MF only change when you will be changing the composition of alloy. Based on the cooling curve, it won't be changing MS and MF. Okay, so for particular both of these MS MF will be fixed at temperatures. So these are two cooling curves that are plotted with different cooling rates. One is the slow cooling curve, other is moderately rapid cooling curve. So this corresponds to normalizing, this corresponds to full annealing. So in this curve it is encountering coarse pearlite, and this part is encountering the fine pearlite. Okay, so this dashed line, it is denoting the transformation that's taking place. So two cooling rates, slow and fast, shown on the CCT diagram. In continuous cooling, bainite is not formed as the transformation to pearlite would have finished before it reaches the bainite temperature. Okay, so in this case bainite can't be formed because by cooling rate you can't bring it to the below this nose temperature. So your all the transformation can only have pearlite in this case. The transformation terminates along the AB curve. So here again these are shown. So 140 degrees Celsius per second is the critical cooling rate. So if you are cooling your steel at a rate which is higher than this cooling rate, above 140, then you will always be getting 100% martensite. Okay, you won't be getting any stable phase. And if you are cooling at higher rate, then you will be getting pearlite. Okay, at a rate which is slower than this. So you will be forming pearlite, which can be coarse or fine depending on the rate. Next is CCT diagram of an alloy steel. So in case of some alloy steel, you can get bainite bay as well. So in this case you will be having a different bay for bainite, where you can form bainite with the help of continuous cooling as well. So carbon and other alloying elements, they shift the perlite and bainite noses to longer times. So if you keep on adding some alloying elements and carbon, so this particular nose, it will shift at longer time, so it will shift to this side because of the less ease for the diffusion. So it is more likely to form martensite if you have more amount of alloying elements. Okay, so bainite formation is also possible for non-eutectoid plain carbon steels. So if your steel is not plain carbon steel, then you can form bainite as well with the help of continuous cooling. And here the continuous cooling diagram shown is for 4340 type of steel. Okay, so here various cooling curves are shown with the different cooling grades. Okay, so the slowest cooling curve is with the dark blue color, having 0.006 degrees Celsius per second. Okay, so it is near full annealing type of cooling. So as you use this cooling rate, then you are getting a structure which will be having both ferrite and perlite. Okay, so if you cool faster than this 0.02 degrees Celsius per second, then you are coming from this side. So here you are forming austenite plus ferrite, and then remaining is converting into bainite, then bainite, and then you are getting martensite as well, remaining part. So you are getting martensite, ferrite, perlite and bainite. At this light blue color, you are getting to the nose temperature, so you are not converting it into stable phases, so you are getting remaining bainite and ferrite, and in this region you won't be forming any stable phases, so you are getting bainite and martensite. Okay, and if you are cooling faster than this critical nose which is near bainite, then you will be only getting martensite, and between this and this you will be getting both austenite. This austenite will then be converted into perlite, this will be converted into bainite and martensite, and remaining is ferrite. Next is heat treatment. So it can be defined by a combination of heating and cooling operations which are timed and applied to a metal or alloy in the solid state in a way that will produce desired properties. The basic heat treatment of steel involves transformation or decomposition of austenite. The final properties, physical and mechanical, of heat treated steel depend on the nature and form of the transformation products. First step is heat the steel above a critical temperature to form austenite. Then the rate of heating to the desired temperature is not important in many cases. Okay, so heating rate only required in case of when your material has some distortion already existing or some residual stresses. However, highly stressed material due to cold working should be heated slowly compared to stress-free steels to avoid distortion. Practical rule: heating to be done as slow as possible to avoid any ill effects. Then in annealing, material is exposed to elevated temperature for a long time and then it is cooled slowly. So mainly furnace cooling. The annealing is carried out to relieve stresses, increase softness, ductility and toughness, produce a specific microstructure. Okay, so there is stress relief annealing. There is also in case of full annealing, you increase softness, ductility and toughness. You can also produce a specific type of microstructure. So for example, in case of diffusion annealing, you reduce coring type of effect, or in other annealings as well you can get aqueous type of microstructure. A variety of annealing heat treatments are possible, characterized by the changes induced in the microstructure and mechanical properties. Now this is the heat treatment cycle or annealing thermal cycle. So here these are the steps of annealing. First step is heating. So you are heating your material, changing the temperature with the time. So heating to desired temperature, then holding or soaking at that temperature. So hold or soak time is there. After that you will be cooling with the controlled cooling rate. So cooling down to room temperature. The time is an important parameter in these processes due to the thermal gradient which exists in the interior and exterior of material. Okay, so in case of tempering, you are cooling it up to lower temperature, very below to lower critical temperature. Okay, so here you are holding, then you are cooling. In case of heating, here annealing, you are heating, holding, then with different cooling rates you can get annealing, then you can get normalizing, then you can get quenching. Then you have iron carbide diagram in the heat treatment temperature range. You have different types of annealing: full annealing, spheroidizing, stress relief annealing, process annealing and normalizing. In case of normalizing, you are heating to higher temperatures compared to annealing. Then you have full annealing for hypoeutectoid steels. Now this is the composition that we have chosen, up to 0.2% of carbon. Here firstly you have a structure which consists of perlite and ferrite, then you are heating it. So when you heat it up to this temperature, you will be getting that the perlite will convert into austenite, okay, and the ferrite will still be in form of this ferrite. So ferrite will start to convert up to this temperature, then it will keep on converting into austenite up to this temperature, then you will be having complete austenitic type of structure. So the higher the temperature that you take it, the higher will the coarser will be the grain size. So after the desired after that desired time or temperature hold, you cool it with the furnace cooling. So here heat the steel to proper temperature and then cool slowly through the transformation range in the furnace. Purpose is to refine the grain, induce softness, improve electrical or magnetic properties and improve machinability. Then it is very slow cooling process, hence close to iron carbide equilibrium diagram. So you can predict what will be the composition of these phases as well. Heat treat a coarse grained 0.2% carbon steel to refine the grain size. So this is one of the examples. Okay, after this you are cooling it to room temperature and you are getting this type of structure. You have pearlite grains, you have and ferrite grains. So this structure is more refined compared to the initial structure. In this case, no change in microstructure occurs during heating until A1. So up to this A1 temperature, which is lower critical temperature, so at A1, pearlite areas will transform to small grains of austenite through eutectoid reaction, and the original large ferrite grains, they remain the same. And if we cool from the temperature, from this temperature, the grain refinement doesn't happen. Okay, and the continued heating between A1 and A3 allows the large ferrite grains to transform to small austenite grains. And above A3, you will be having a microstructure with small grains of complete austenite. Then you will be moving to the subsequent furnace cooling, which results in small grains of pro-eutectoid ferrite and small areas of coarse lamellar pearlite. Then the proper annealing temperature for hypoeutectoid steel is 500 degree Fahrenheit above A3 line. Then we have hypereutectoid steels. In this case, refinement of grain size for hypereutectoid steels occurs at 500 Fahrenheit above the lower critical temperature A1. The heating above this temperature will coarsen the austenitic grains, which on cooling will transform to large pearlitic areas. The microstructures of annealed hypereutectoid steel will consist coarse lamellar pearlite areas surrounded by a network of pro-eutectoid cementite network. And this excessive cementite network is brittle and it tends to be a plane of weakness. Hence, annealing should not be final heat treatment process for hypereutectoid steels. Presence of thick, hard grain boundaries will also result in poor machinability. Now, approximate tensile strength of annealed hypoeutectoid steels may be determined by the proportion of ferrite and pearlite present. Approximate tensile strength can be given by 40,000 times the percent ferrite plus 120,000 times the percentage of pearlite and steel divided by 100. And annealed 0.2% carbon steel contains approximately 25% pearlite and 75% ferrite, whose approximate tensile strength is 60,000 psi. Okay, so this 25% and 75% ferrite and pearlite, this you can get by using tie line and Lever's rule. The same formula can't be applied to hypereutectoid steels since their strength is determined by continuous cementite network. Next process is ferrodizing. In this case, it is annealed hypereutectoid steels which have poor machinability due to the microstructure, which is pearlite plus cementite network. And since cementite is hard, the cutting tool can't cut through these plates. Spheroidizing produces a spheroidal or globular form of carbide in ferritic matrix, which can be shown here. So spheroidized cementite in a ferrite matrix. So for prolonged time at elevated temperatures, it will completely break up the pearlitic structure and cementite network. The cementite becomes spherical, which is the equilibrium geometric shape. One of the methods of spheroidizing, so firstly, prolonged holding at a temperature just below A3 or heating and cooling alternatively between temperatures that are just above and below A1, heating to a temperature above A1 and then cooling very slowly in the furnace, or holding at a temperature just below A1. The spheroidized structure is desirable when minimum hardness, maximum ductility or maximum machinability is important. So sometimes it's also performed that after spheroidizing the structure, you perform machining and then you provide another heat treatment to the product for getting desired microstructure. Low carbon steels are seldom spheroidized for machining, as in the spheroidized condition they are excessively soft. The cutting tool tends to push the material rather than cutting it. So it can't be used for low carbon steel. It is basically used for high carbon steels. Too long exposure to spheroidized annealing temperature leads to coalescence of the cementite particles to form elongated structures, which in turn leads to reduced machinability. Then spheroidite. Spheroidite forms when pearlitic benitic steel is heated and held at a temperature below eutectoid for a sufficiently long time. Example is at 700 degrees Celsius for 18 to 24 hours. Cementite phase appears as sphere-like particles. So as shown here, Fe3C cementite, and remaining white part is alpha ferrite. This transformation happens by addition. Here Fe3C phase appears as sphere-like particles embedded in continuous ferrite matrix, and this transformation happens by additional carbon diffusion with no change in compositions or relative amounts of ferrite and cementite phases. Here a two-phase microstructure consisting of spheroidized carbide and ferrite, which is formed by heat treating pearlite, benite or martensite at a temperature below the eutectoid temperature. Then we have stress relief annealing. So stress relieving is a heat treatment process which helps to remove the internal stresses caused to the metal when it is machined, cast, rolled or forged. It typically involves placing the metal into a set temperature for a certain amount of time. Then the metal is cooled using a controlled method. Stress relieving must be done carefully to remove the stresses without impacting the metal's properties, which should be kept for the part. This treatment can be done for both ferrous and non-ferrous metals. And the heating cycle is shown here below low critical temperature. Then we have process annealing. In this case, a steel is heated below the critical temperature and then keep it at a temperature for a while, then cooled slowly. It is also called subcritical annealing. It is suitable for low carbon steel. Phase transformation is not involved in this process. The material is in the same phase in throughout the process. The process annealing is cheaper than the full annealing, and it is used in sheet metal and wire industries, and it is done during the cold rolling or wire drawing operations in between those. Then we have normalizing. Normalizing is carried out by heating steel to 1000 degree Fahrenheit above A3 upper critical temperature, followed by cooling in still air to room temperature. Purpose is to produce harder and stronger steel than full annealing. For hypoeutectoid steels, it is necessary to heat above ACM line in order to dissolve the cementite network. Normalizing may also be used to improve machinability, modify and refine cast dendritic structures, refine the grain and to homogenize the grain structure. The increase in cooling rate due to the air cooling as compared to furnace cooling affects the transformation of austenite and the resultant microstructure. In case of iron, iron carbide equilibrium can't be used to predict the proportions of pro-eutectoid ferrite and pearlite or pro-eutectoid cementite and pearlite, as the cooling is not done under equilibrium conditions, and there is less time for formation of pro-eutectoid constituent. Hence there will be less pro-eutectoid ferrite in normalized hypoeutectoid steels and less pro-eutectoid cementite and hypoeutectoid steels. In hypoeutectoid steels, sometimes the cementite network may be absent altogether. Hence normalizing increases the strength of hypoeutectoid steels. Normalizing also affects the temperature of austenite transformation and the fineness of pearlite. So faster the cooling rate, it leads to lower temperature of austenite transformation and finer pearlite. The difference in spacing between cementite plates and pearlite is shown for annealing and normalizing. Here it's shown that the spacing is also higher and the plate thickness is also higher compared to normalized. Cementite plates are closer together in the case of normalized medium pearlite. They tend to stiffen ferrite, so it will not yield easily, thus increasing hardness. Normalizing also produces finer and more abundant pearlite structure than that of annealing, which results in harder and stronger steel. Next is hardening. So under slow or moderate cooling rates, the carbon atoms are able to diffuse out of the austenite structure. The iron atoms then move slightly to become BCC. The gamma to alpha transformation takes place by a process of nucleation and growth and is time dependent. With increase in cooling rate, there is less time for carbon to diffuse out of the solution. Although some movement of iron atoms take place, the structure can become BCC while the carbon is trapped in the solution. The resultant structure is called martensite, which is a supersaturated solid solution of carbon trapped in a body-centered tetragonal structure. So this is a BCT type of structure having a C/A ratio. So here the two dimensions of the unit cell are equal. Here A and B are equal and C is different. And third dimension is elongated because of trapped carbon. The axial ratio C/A increases with increase in carbon content to a maximum of 1.08. The highly distorted lattice structure is the prime reason for the high hardness of martensite. Atoms of martensite are less densely packed than austenite, and hence an expansion occurs during the transformation. This expansion produces high localized stresses, resulting in the matrix's plastic deformation. After drastic cooling, martensite appears microscopically as a white needle-like acicular structure, which is often described as pile of straw. Martensite transformation. So the transformation is diffusionless and there is no change in chemical composition. The small volumes of austenite, they suddenly changes its crystal structure. The transformation proceeds only during cooling and ceases if cooling is interrupted. Hence the transformation depends only on the decrease in the temperature and is dependent on the time. The transformation of the above type is called a thermal, in contrast to one that will occur at a constant temperature. So as I think previously, we saw here ms, after this point, ms point, if you keep on increasing if you put it here and you leave it for prolonged time, it won't change the structure, and the martensite percentage will be at a percent of this particular temperature. So this martensite transformation is dependent on temperature. So up to you bring up to here this temperature, only then you'll see 100% martensite. It won't change with the time as it occurs in the other of the phases such as perlite, bainite, which are time dependent because they consist of diffusion rather than a thermal type of transformation in case of martensite. Okay, so hence the transformation depends only on the decrease in temperature and is independent of time. The transformation of the above types is called athermal, in contrast to one that will occur at a constant temperature. So as shown here, your austenite will directly convert into martensite. And if you have austenite after you have moved to the single phase region, then you have three options. You can either slow cool in furnace cooling, then you will be getting perlite plus pro-eutectoid phase, which can be pro-eutectoid ferrite or it can be pro-eutectoid cementite based on the composition of steel. So this will be furnace slow cooling, then it will be normalizing and annealing. Moderate cooling, you can have bainite, which can be occur in austempering. Okay, so you can get this bainite. You can get rapid quenching, then you can get complete martensite type of structure, but you cannot get 100% of martensite. You will always be having some retained austenite percentage up to 2% or so. Okay, we'll go through questions once again. So first question was the welding defect of lack of penetration can be taken care of. Answer options for by increasing welding speed, by increasing current value, by reducing current value, or by opting low heat energy source. So correct answer will be by increasing the current value. Okay, because increasing welding speed will have adverse effect on the penetration of the material to the weld. So the incomplete penetration occurs when the weld bead does not reach the root of the joint of the weld on the opposite surface of the part. And to correct this, you can increase the current, decrease the welding speed, or change the joint geometry. Next question is the welding defect, which causes a reduction in the cross-sectional area, so reduces the strength of the welded joints. Your options are residual stress, distortion, undercuts, and misalignment. So the correct answer will be undercuts. So undercut is a welding defect which reduces the cross-sectional area of the base metal, which in turn weakens the weld and workpieces. Undercutting is most common in lap fillet welds, but also can occur in other type of joints, and this is what it looks like. And some of the causes for this type of defect is the excessive current, poor technique, incorrect filler metal, incorrect angle, too large of an electrode, or incorrect usage of gas shielding. Next question is the strengthening mechanism which can lead to the hard phase formation due to the heat treatment of steel. Okay, so answer will be, your options are solid solution strengthening, grain refinement, transformation hardening, and dispersion hardening. So the correct answer will be transformation hardening. So transformation hardening can be defined as the, which is also known as quench hardening, is a process which improves the mechanical properties of steel by rapid quenching a heated steel surface. This process involves a diffusion-less martensitic transformation which occurs when steel is quenched too quickly from the austenitic phase. Some of the ways to transform are laser transformation, friction transformation hardening, and flame hardening. Fourth question is the annealing and normalizing is done. Your options are above low critical temperature, above upper critical temperature, above eutectic temperature, or all of these. So correct answer will be, of course, above upper critical temperature. So full annealing produces a softer microstructure, and the temperature for full annealing are typically 50 degrees Celsius above the upper critical temperature A3 for hypoeutectoid steels and lower critical temperature A1 for hypereutectoid steels. And for normalizing, it is 55 degrees Celsius above the upper critical line. Okay, and the normalization temperature is higher than the temperature for full annealing. On the other hand, the cooling is more intense. Normalizing improves the machinability of component and provides dimensional stability if subjected to further heat treatment processes. The main difference is with the how it's cooled, and in case of annealing you cool it in controlled rate with furnace. In normalizing you cool in air. Fifth is correct statement regarding the effect of soaking temperature during normalizing of steel on grain sizes. So your options are, higher the soaking temperature, the finer the grain. Higher the soaking temperature, the coarser the grain. The lower soaking time, coarser will be the grain. The lower the soaking temperature, the coarser the grain. So the correct answer will be second one. Okay, so with increasing both time and temperature, you increase the grain size because there will be more time and temperature for diffusion, more activation for diffusion. Okay, so more diffusion will lead to the grain coarsening. Next question is the temperature range in the heat treatment of steels for stress relieving purpose. Options are 1050 degrees C, 1150 degrees C, 600 degrees C to 650, above 1200 or below 500 degrees C. So above 1200 degrees C you will be having diffusion annealing. Okay, and process annealing will be around 500 degrees Celsius. Okay, and stress relieving will be between 600 degrees Celsius and 650 degrees Celsius. So B will be the correct answer. Okay, so the temperature range for stress relief annealing of steel is usually between 550 degrees Celsius and 650 degrees Celsius, and the exact temperature depends on the composition of steel. Okay, and stress relief annealing is used to relieve stresses from cold working. In contrast to process annealing, this heat treatment is usually performed after the product has been made, and care must ensure uniform cooling, particularly when a component is composed of variable section sizes. If the rate of cooling is not constant and uniform, new residual stresses can result in equal to or greater than those that of the heat treating process intended to relieve. Next question is weldability of a metal depends upon. Your options are thermal conductivity, thermal coefficient of expansion, melting point density, melting point temperature and density. So the correct answer will be 1, 2, 3 because density doesn't affect the weldability of metal. Okay, so the weldability can be defined as the how easily material can be welded without defects. Okay, defects, the factors are material properties and welding method, welding parameters and shape of parts. So geometry of the weld can also affect weldability. Eighth is the most effective strengthening mechanism in case of heat treatable aluminum and copper alloy is. Your options are solid solution hardening, grain refinement, transformation hardening, precipitation hardening. So answer will be precipitation hardening. So aluminum copper always forms in at lower composition of copper. It will form precipitates of aluminum copper. Okay, so this is precipitation hardening, and because of that it can show strength as comparable to the steels as well because of this hardening. Ninth question is the heat treatment process used to reduce the effect of strain hardening during the cold working process is. Your options are spheroidized annealing, process annealing, full annealing and intercritical annealing. Correct answer will be process annealing. So process annealing is also known as subcritical annealing or intermediate annealing, heat treatment process which improves the properties of metal alloys. Process annealing improves the cold working properties of low carbon steel and softens high carbon and alloy steels. It can also relieve internal stresses, restore ductility and make parts more workable. The process involves heating the metal and alloy to a predetermined temperature, hold it for a set amount of time and then cooling it to room temperature. Range of process annealing is typically between 260 to 760 degrees Celsius depending on the alloy. It is mainly used for low carbon steels such as cold rolled steel, wire drawn steel and centrifugally cast ductile iron pipe. 10th question is the reason for using normalizing heat treatment on steel is reduction of residual stresses, refinement of grain structure or increment of residual stresses. So correct answers will be first and second. So as we know, normalizing improves the strength of material, it refines the grain structure and it also reduces the residual stresses, also relieves the stresses. It also provides uniform microstructure, provides durability, provides ductility because of the fine pearlite formation. Okay, and normalizing is also less expensive than annealing because during normalizing you will be cooling your material outside the furnace, so you will be requiring less time in furnace, and also in case of normalizing you don't require any further heat treatment after this, so that's why also it will be cheaper compared to full annealing. Normalizing is one of the most common industrial processes for metals and it is used for hot rolled products like bars, railroad wheels and forged steel products. Then we went through these lectures. First we talked about weldability and welding defects. Okay, then we went through heat treatment fundamentals, annealing types, then annealing, normalizing and hardening. Then we went through how to read CCT diagram and triple T diagram and differences between annealing, normalizing and hardening and tempering, spheroidizing, stress relief annealing, process annealing. martensite formation. So that's it from my side.